this video, we'll use the integral test to talk about a very important class of examples, and those are called p-series. So let's start with the example where S equals a sum from n equals 1 to infinity of 1 over n. We actually mentioned before that this series diverges. Why did we mention that? The divergence test says that if you have a bunch of things you're adding up, an, and the limit as n goes to infinity of an is not 0, then your series diverges. And I said at the end of the videos for section 11.2 that the converse is not true. There are examples where you have a sum of things, an, and the limit is equal to 0, but the series diverges anyway. So if the limit of an is equal to 0, that doesn't tell you anything. You still have to do some other tests to tell if your series converges. And the example that I gave of that was this series. The limit as n goes to infinity of 1 over n is equal to 0, but we're going to see that this series diverges. Okay, well, how are we going to see that? We're going to see that with the integral test. So we're going to let f of x be equal to 1 over x. This is decreasing. It's non-increasing from 1 to infinity. It's continuous. The only problem with this function is it's 0, but it's continuous from 1 to infinity. And it's positive. That's clearly true. So we're going to tell whether or not this series converges by looking at the improper integral from 1 to infinity of f of x dx, which is the limit as t goes to infinity of the integral from 1 to t of 1 over x dx. And this is an integral we know how to do because we know an antiderivative of 1 over x. So this is a limit as t goes to infinity of natural log of x evaluated at t and at 1. Again, I'm not worrying about putting in absolute value of x because I know t and 1 are both positive. So this is a limit as t goes to infinity of natural log of t minus natural log of 1. Natural log of 1 is 0. So this is just the limit as t goes to infinity of natural log of t. And this diverges. This goes off to infinity. So by the integral test, this series S, the sum from n equals 1 to infinity of 1 over n, which is like 1 over 1 plus 1 over 2 plus 1 over 3, this diverges. It goes off to infinity. There's a section in 11.3 of Stewart's book that's about estimates of sums. We're not going to talk about that in this course, but there is some question about, okay, this goes off to infinity. How fast does it go off to infinity? And you can get some information by looking at this improper integral. The sum of the first however many terms, like the terms up to n equals x, is roughly equal to natural log of x. But that's the kind of thing that you can worry about in a future course. Okay, so this is one example of you're adding up a bunch of things that go to 0, but that series diverges anyway. Let's look at another example. Let's look at S equals the sum now not of 1 to infinity of 1 over n, but of 1 over n squared. So we're going to let me move this over. We're going to let f of x be equal to 1 over x squared. And it's clear that this is non-increasing, continuous, and positive from n equals 1 to infinity. Checking these three properties is often really easy. Like you just look at this function and say, well, as x gets bigger, the denominator gets bigger, so the function gets smaller. This is continuous because the only problem is at x equals 0, and it's clearly positive. like to check these properties, I often wouldn't write anything at all, but I do want to get into the habit of encouraging you to like actually check that you can apply the integral test. Okay, so now we're going to look at the integral from 1 to infinity of f of x dx, which is the limit as t goes to infinity of the integral from 1 to t of 1 over x squared dx. And we know an antiderivative of this function, t goes to infinity of minus 1 over x at t and at 1, which is the limit as t goes to infinity of minus 1 over t minus 1 over 1. As t gets really large, minus 1 over t goes to 0, minus 1. This is something going to 0 plus 1. This is 1. So by the integral test, this series S converges also. And now, let me make this point that this does not say that the series also converges to 1. It doesn't. I mean, we get 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, which is 1 plus 1/4 plus 1/9. So it's definitely bigger than 1. This series converges to something, and that something definitely isn't 1. And this integral test is not going to tell you what it converges to. Okay, this is one of my favorite facts in like all of mathematics, so I'll tell you what this converges to. This converges to pi squared over 6. Proving this is actually very hard. So if you take math 147, which is complex analysis, you would pick up the tools that would show you that this series actually converges to pi squared over 6. We will not worry about that now. It's enough to know that it converges. So I'll just point out, if you go to my website, on one of the pages I have a list of my favorite numbers, and pi squared over 6 is, I think, tied for my second favorite number. It's a really good one. It comes up all over the place in the kind of number theory that I study in my research life. Okay, so we've looked at the example of a sum from n equals 1 to infinity of 1 over n to the first power. That diverges. And we've seen the example of sum from n equals 1 to infinity of 1 over n to the second power, and that converges. So what about the sum of 1 over n to the pth power for other values of p? I'll pause and erase, and then I'll tell you what happens in general for this class of examples that are called p-series. Here is this really important fact that we're going to use over and over again throughout the rest of the course. What is a p-series? It's a sum from n equals 1 to infinity of 1 over n to the pth power, where p is some real number. This converges if p is bigger than 1. We already saw p equals 2, that this converges. And it diverges if p is less than equal to 1. We already saw p equals 1, where we got the sum of 1 over n, diverges. So we saw p equals 2, and we saw p equals 1, and this gives you the answer for all p. If p is bigger than 1, it converges. If p is less than or equal to 1, it diverges. The integral test will tell you that this series converges for p bigger than 1, but it will not tell you what it converges to. So you don't need to know how to prove things like this for this course, but let me just explain why. Why is this true? So recall from section 7.8, when we talked about improper integrals, that the improper integral from 1 to infinity of 1 over x to the p dx, that this integral converges for p bigger than 1, and it diverges for p less than or equal to 1. So why does this series converge for p bigger than 1 and diverge for p less than or equal to 1? Well, we're using this fact from section 7.8 plus the integral test. So let me just finish this video by saying this tells us a bunch of other things, like the sum from n equals 1 to infinity of 1 over square root of n. This diverges because this is a p-series with p equals 1/2, which is less than 1. So p-series are really important. I said in the last set of videos that geometric series were some of our building block series that we really understand well. P-series are another one of those foundational building block series that we understand well. So in future lectures, we're going to see that sometimes you can tell whether or not a series converges by comparing it to one that you know well, something like a p-series or a geometric series.